Hello there, my name is David Kidder. In this video we're going to take a look at how to calculate the impedance, the current, and the total powers in an RL circuit. So what I have here is a real true-to-life coil. It has a value of inductance of 100 millihenries, and it also has a resistance inherently built into the inductor due to the very thin wire being used, and it has a resistance of 20 ohms. So that's a measurable resistance. So what we want to do is figure out what's the total impedance on the AC circuit from that coil, and what's the current that flows through it. So the first thing we got to do is just figure out what the value of XL is. And so we have 100 millihenries, and XL is equal to 2 pi FL. Our frequency is 60 hertz. Our inductance is 100 millihenries. And when we calculate the value of XL, we get 37.699 ohms. All right, so our XL is almost 38 ohms. So now that we have each value of the current limiting effects, the resistance, and the XL, we can go ahead and put it into a impedance triangle. So this is a very straightforward operation. It's a very easy task to solve the impedance of a circuit with this triangle, right? So first thing we got to do is plot everything out. The resistance is going to go onto the base, and the XL is going to go onto the vertical component. Okay, so there's a 90-degree relationship between the ohmic value of resistance and XL because of the 90-degree phase displacement between their volt drops, and so they don't act on the circuit at the same time, and so we don't add them directly, we add them with 90-degree relationship. All right, so simply just put in our numbers. The R of the coil is 20 ohms, and our XL is 37.69. So the last thing that we have to calculate then is the hypotenuse, which is the total impedance of the circuit, in this case, the Z total. Using Pythagorean theorem, we can solve for Z, and we get 42.676 ohms. All right, so we don't have 57.699, which would have been the result if we added R directly to XL. We only have 42, and we sort of see there's a bit of overlap when there's both R and L in these circuits. But they don't add up directly. It's this 90-degree relationship, all right? So from that point, then all we got to do is figure out what the current of the circuit is. And so I'll step over here, and the current is going to be the E total, which is our source, divided by the Z total, which is our total impedance. So these are all circuit totals. I total is equal to E total over Z total. All right, so we just simply punch in the numbers, 120 volts. Divided by our Z total of 42.676 ohms, and we get a current total of 2.812 amps. All right, so very straightforward. Just remembering that there's that 90-degree relationship between R and XL will yield us the Z. Once we have our new Z, Ohm's law still applies. We're just using our Z total now because we're in AC, and AC has reactance, where it's DC doesn't have reactance. All right, so that's our new current. Now, last thing we're going to do in this video is figure out the power of this circuit. And so a very easy way to figure out power when you have this set up is just simply take this existing triangle and multiply each side by I squared. So for example, if I have I squared times R, I get my power in watts. If I have I squared times XL, I get my quadrature power due to the XL. And if I take I squared times Z total, I get my total apparent power of the circuit. So I just need to take this same triangle, multiply each side by I squared, and I'll have all of the power values for my triangle that I need, or for my circuit. All right, so just go ahead and do that. I'll try and draw the exact same triangle. All right. And we just simply do 20 ohms times 2.812 squared, so I squared times R will get us the power total of our circuit. All right, and so that's 158.15 watts. So I'll write that out again. Power total is I squared times R total. There we go. And seeing as we're in series, the current is constant through everything. It's the same through all the components. All right. For our Q of XL total, it's simply just I squared times XL total. And so that'll be 2.812 squared times 37.699. And we get a quadrature power total of 298.01 bars. All right, so funny looking one. There we go. 298.01 bars, volt amp reactive. Okay, so those are our two base units, the watts and the vars. And when we combine them together, just like we did up here, to get impedance, we get our apparent power total. So that's the sort of the impedance of the power. All right. The sort of to liken the two, it's sort of the same kind of value. It's a total circuit property. So we can do I squared times Z total. We can also just simply do I times E. So 120 volts times 2.81 will get us the same value as this. So S is equal to I times E. Same formula, just a different way to do it. But seeing as we already have Z and we are just multiplying everything by I squared, why not just carry that all the way through? All right, so 2.812 squared times 42.676 is going to give us our S total. That's 337.454 VA. All right, so that is the total circuit power in this situation. A couple of things that we just want to remember. L and R don't behave at the same time. They happen 90 degrees apart, so we have to treat them with respect to their 90-degree relationship, find the total impedance of the circuit, then we can go ahead and get current. Once we have current, we can go ahead and solve for all the power in that circuit. All right, so hopefully you found this interesting, if not educational, and we'll see you in the next video.